The dot product. Imagine pulling a wagon. The force vector would be here on an angle, but the displacement vector would be horizontal. So if we looked to combine these two vectors, the force that you're applying is not all of that force would be applied to actually move the wagon horizontally. So we could go ahead and look here and see the portion of that force vector that would be applied in the displacement vector's direction. Now we could use a little bit of trig here to connect these, and the cosine of this angle between the force vector and the portion of the force vector applied to the displacement being theta, then we know that cosine theta is going to be adjacent over hypotenuse. So we could take the magnitude of the component of the force vector in the v direction over the magnitude of the force vector. Now we could then solve that for the magnitude of the force in the v direction here, and we would have this. Now we are going to return to this idea then after we visit the idea of, okay, so how would we find the angle between two vectors? So this could be in 2 dimensions or 3 dimensions. We could have these vectors and we were interested in finding this angle between them, and we're going to actually look in R3. So here are 2 vectors, v and u, and an angle between them. What we're going to do is we are actually going to put a third vector here to make a triangle, and we're going to use the law of cosines, which says the length of one of the sides squared, so we'll use magnitude here, equals the sum of the lengths of each of the other sides squared minus 2 times the product of those other 2 sides times the cosine of that angle between those 2 sides. So that's the law of cosines. Let's solve this for the cosine term. And now we're going to do a couple other things so we can write the right-hand side in component form. So first of all, let's put another couple of vectors on here so we can see that w would equal u minus v. And if we wrote that in component form with a 3-component vector, u would be u sub 1, u sub 2, u sub 3, and v sub 1, 2, and 3. So we could express that in its component form like this. Also, an expression for the magnitude squared of a vector, we're looking to see we have that 3 different times here. That would just simply be each of the components squared and then taking the sum. So let's replace this right-hand side with the various pieces that we have here. So first of all, we have this magnitude of u squared, so that would be u1 squared plus u2 squared plus u3 squared, and then plus the magnitude of v squared, so that's v1 squared plus v2 squared plus v3 squared, and then minus w1 squared plus w2 squared plus w3 squared. Okay, and so this negative will apply to each of these components. Now we have that w equals this in its component form, so we could go ahead and express that. So we would have u1 squared plus u2 squared plus u3 squared plus v1 squared plus v2 squared plus v3 squared minus, and here we'd have u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. And if we multiply this out, this would be u1 squared, but this negative would apply to it, so minus u1 squared. Middle would be negative 2u1 v1 with the negative applied would be plus 2u1 v1, and last times last would be plus v1 squared, then the negative applied minus v1 squared. Now we can continue that pattern for looking at each of these, so we'd have minus u2 squared plus 2u2 v2 minus v2 squared minus u3 squared minus or plus 2u3 v3 and minus v3 squared. So what I did was replaced just that last part with this, and we could see that these would cancel, and we could see that these would cancel, and the u3 squareds, the v1, the v2s, and v3 squared. So let's express what we have left, which would be right here 2 magnitude of u magnitude of v cosine theta equals, looking here at what we have left, we have a 2 and everything. We have u1 v1 plus u2 v2 plus u3 v3, factoring that 2 out. And now we see that the 2's would cancel, and we could solve this for cosine theta by dividing by these two magnitudes. So what we end up with is a formula then, because we could take the inverse cosine for finding the angle between the two vectors. It's inverse cosine of, here is our product of u1 v1 u2 v2 u2 v3 summed divided by this magnitude. Now we are going to express this then, we're going to give this a special name and have a special notation when we multiply components but then add between like that. This is called the dot product. So given two vectors, the dot product, and we express it with a dot between them, is defined as multiplying corresponding components and summing them up. This is also sometimes called the inner product or the scalar product. Called the scalar product because you're taking two vectors and you're doing some kind of a product with them, but you are getting a number or a scalar when you do that. We can also combine this idea then when we derive this to have a formula for the angle theta between two non-zero vectors then. The angle between the two vectors would be the inverse cosine of the dot product of the two vectors divided by the product of their magnitudes. So let's go ahead and find the angle between these two vectors. This is what these two vectors look like, and we would find this angle between them. So we know the cosine of the angle between them equals the dot of the two. So we take 1 times negative 2, which is negative 1, plus negative 3 times 5, which is negative 15, plus 2 times 1, which is 2. And then we divide that by the magnitude of A. Well, the magnitude of A is going to be the square root of 1 squared plus negative 3 squared, which is 9, plus 2 squared, which is 4. So it looks like that magnitude is going to be the square root of 14. And if we do the magnitude of B, that's going to be the square root of negative 2 squared, which is 4, plus 5 squared, which is 25, plus 1 squared. So combining those, we would have square root of 30. So cosine theta is going to equal this. So theta is going to be the inverse cosine of, it looks like this is going to be negative 14 over the square root of, let's see, that's 420. We would then go to a calculator and put that in to get an approximate for the angle between these vectors. So when we do that and we do inverse cosine of this, we get 2.32 radians. And if we did that in degrees, because we're trying to get a sense of this if we don't have as good a feel for how big a radian is compared to a degree, this would be 133.1 degrees. So let's find the angle between these two vectors. So the angle between these two vectors, it would be cosine of theta equals, if we do their dot product, we get 3 times 6, which is 18, plus 2 times 4, which is 8, over the magnitude of V. So magnitude of V is going to be square root of 9 plus 4, so square root of 13. And then we need the magnitude of W, which is going to be the square root of 6 squared plus 4 squared. So that's going to be the square root of 52. Now when we do inverse cosine of this, this would be 26 over square root of 13 times 52, we get 0. So what does it mean when the angle between the vectors is 0? Well, let's look at these vectors. And here is V, here is W. Oh, and if we looked at that, we'd seen one is a scalar multiple of the other. Now, these vectors are shown here as position vectors, but we could put equivalent vectors somewhere else and have a look here. And so essentially what it means when the angle between the vectors is 0 is that those vectors are parallel to each other. So now let's show that these two vectors are perpendicular to each other. Well, if we have cosine theta equals, we're going to dot the two vectors together. 2 times 5 is 10, plus 2 times negative 4 is negative 8, plus negative 1 times 2 is negative 2, over, and we have the magnitudes, which we actually don't really even need to compute because we see that the numerator is 0. But so this would be magnitude of the two vectors, and we would get 0. Well, when is the cosine 0? If you think about that, it is when the angle between them is 90 degrees, or pi over 2. So these vectors are perpendicular to each other, and we also use the word orthogonal when we're talking about vectors, and that just means that those vectors are perpendicular to each other. So when did that happen? It happened when this numerator ended up being 0, and that was the dot product between the two vectors. So two vectors u and v are orthogonal if and only if their dot product is 0. And we know with if and only if this will work in either way. So if the dot product is 0, they are orthogonal. If they are orthogonal, then the dot product of the two vectors is 0. And remember, orthogonal just means perpendicular. So let's go ahead and look at two vectors here. And as we look at these two vectors right now, as we look at this right-hand side, we get 2. And that is simply because the cosine is 1, and then we're multiplying them by their magnitudes. Now, as we change the angle between these vectors, watch the dot product. So here below we are graphing the dot product, and up here we see that we have the combination of cosine theta and the magnitude of A, magnitude of B, which is the dot product. And we see that that dot product is positive. We see that it is decreasing as we do this, and as we continue and we get over here until we can get these vectors to be orthogonal or perpendicular to each other, that is when we have that dot product being 0. So there they are at 90 degrees, or pi over 2 from each other. Now as we continue and we now have an obtuse angle, look what happened to the dot product. The dot product is now negative. And so a negative dot product when we dot two vectors lets us know that the angle between them is obtuse. And the larger the magnitude of this, or so that the more this is negative, we see that the larger the angle here. So now we started at 2 when they were parallel to each other, going in the same direction, and now when they are going in opposite directions, we see that we have negative 2. So let's just summarize what we just saw there. So if we have the angle between two vectors and that angle is acute, the dot product is positive. If we have the angle between those two vectors being pi over 2 or 90 degrees, the vectors orthogonal, the dot product is 0. And if the angle between them is obtuse, the dot product is negative or less than 0. So some properties of the dot product, and these are easy to see if you just write out essentially what they mean. But if we dot vectors together, then we have the magnitude squared, because we know when we dot these together that this is just simply that when we dot them, we do first component times first component plus second component times second component plus third component times third component. If those components match, we have the magnitude squared. It doesn't matter which order it commutes, because when we dot these, we are just simply doing real number multiplication, and that is commutative. It also is distributive. It also then is associative with a scalar, and all of these are based on, because when we do the dot, we are working with multiplying and adding real numbers. And if you dot with the 0 vector, you get 0, and that would simply make sense because the 0 vector would be a vector whose components are 0, and if you dot that with a vector whose components are u1, u2, and u3, you see we get 0 plus 0 plus 0. So this is the 0 vector, and this is the scalar 0. Now let's go back to our wagon problem. We now have a formula for cosine theta. It is dotting the force vector with the displacement vector over the product of the magnitudes of those two vectors. Now we could take this and we could substitute that in then for cosine theta, and then once we did that, we could cancel these out, and so we would have the force vector dotted with the displacement vector over the magnitude of the displacement vector, and that would give us the magnitude of the force vector in the direction of the displacement.